This is CPE 233. Part of lecture 1 here is explanation or a brief introduction to experiment 1. So there's 4 parts to experiment 1. We are only doing part A. So that's 1A. So the description of the problem, pretty straightforward. It's a Fibonacci sequence generator, which essentially, just to make it kind of interesting, we're only generating the odd numbers. Okay, so a little bit misnomer there. We're actually generating whatever numbers you want, but we're populating the RAM with just the odd numbers in the Fibonacci sequence. And so you can see example of the Fibonacci sequence up here. Notice it starts at 1, 1. I want you to start it at 1, 1. Makes things pretty easy. And the idea here is it's going to be 1, 1, 3, 5, 13, 21. It's going to toss out every even Fibonacci number. Okay, so you can see them there, but I crossed them out just, so give you an idea of what's going on here. So what you're going to do is press a button. Once you press that button, it's going to populate that RAM with those numbers and then continually display them. So a couple constraints. There are more constraints in the actual write-up, so be sure to go look at that. But I only want to use digital modules in this. I say this because it's going to make it much more simple, because the modules are there, they're done, they're ready to go, they're written. So additionally, you need some math operators, but I don't want to use math operators. I want you to use the modules out there instead. For example, the RCA Replicare adder has some math operators in it, as do the counters, but and that's okay, because you're going to use those in modules. But I don't want you creating your own modules and using your own, filling them full of mathematical operators. Looks too much like programming. This is still digital design. So you're going to design a circuit, and this circuit is going to be controlled by a state machine. So the state machine, for your state machine, limit it to 10 states, which is more than you need, much more than you need. I want to make that state machine 100% independent of the RAM size, or the sequence length in this case. And additionally, inside that state machine, the only memory in there should be the state variables. Don't add extra memory to your state machine other than the state variables. And so there's few more constraints in the actual write-up, so I encourage you to go read the lab manual in its, at least for experiment 1A. So the Canvas has a bunch of resources out there. These particularly, these are just standard hardware modules, sequential and combinatorial stuff. Most of these things are parameterized, which means you have to override the parameter in your instantiation. I don't want you changing the code in these. I want you to override the parameter in your instantiation. Particularly, there's a RAM module out there. Use that. It's there's actually 2 parameters in it you need to override. Not a big deal. All these modules have a instantiation template in the header. By all means, cut and paste that thing. It's going to make your life real easy. You're not going to make mistakes. There's also an FSM template out there, which I call a cheat sheet. I use that as a starting point. Anytime I have to write a state machine in Verilog, this is my starting point. You should use that too. It's something I understand, and I've used it a bunch, so I encourage you to do the same. There's also a universal 7-segment display driver out there. I use that also. I don't know what you used in your CPE 133 course, but I want you to use this one for 233. There's a couple, I always forget how it works, and that's why I put all the notes of how it works inside the file banner. So take a look at that too. You got to override, you got to select the right parameters to get this working properly for this experiment. So this experiment 1 is, I like to think it's the continuation from CPE 133, kind of like a big circuit with a RAM. But I know that's often not the case, because I know rumor has it that you were not expected to do design in CPE 133, and I think that's Kind of problematic, but now's your chance. We're going to do design in this class. Classic approach for design is taking a top-down approach, which means starting at a high level and working downwards. And this works really nicely because a lot of the modules are provided for you. You're just going to plop those modules in and connect them in such a way that that your circuit works to solve the problem. So step one, understand the problem. Once you understand the problem, you want to start at high level and start selecting modules for your circuits. So this circuit, obviously, it has a RAM. Okay, for this course, anytime I have a RAM, I'm going to address that RAM with a counter. What else? I know I'm going to have that universal 7-segment display device driver, blah, blah, blah. Anyways, just drop those down, put it on a piece of paper, hook it up. Is the next step, once you get all the modules you think you need for this thing, connect them up properly, and then you need to control the data flow through those modules, which is going to be done with the state machine. So the state machine is going to be reading the various status outputs of your circuits and then issuing the proper control signals. And yeah, it's an issue of sitting down and designing a state machine such that it's going to drive your circuit and solve the problem. Now the issue here is, like I said, all these modules are provided. It's your mission to connect them up in Verilog, get it working in Vivado environment, and test it on the board. So a couple ideas here. Understand it. You should design it on paper. I'd say keep it simple. Don't be fancy. My motto is make it work, then make it work good. You're just responsible for making it work. The design process in itself is iterative. You're not going to, I mean, I hope you get it right the first time, but you're probably not. It's understood that you're going to have to go back and fix stuff as you think of stuff, and of course as problems arise, like, you know, such as you forgot to do something. So all this is, of course, is going to be done with Verilog, and then you're going to test on the Basis 3 board. So along the way, by all means, ask questions. Please, I'd love to see your circuit. Show me your diagrams. I'll give you my comments, and I can, you know, I've seen many different designs on this one. Some are very problematic. I'd love to steer you towards the easy, flawless approach on this one. So by all means, talk to me. I'd love to work with you on this. So yeah, use the provided modules. Don't write new ones. Tons of modules out there. A couple important things. All the modules have instantiation templates in the file manager. Use those. Be sure to override the default values. Don't change the circuit. The important thing, do not, so you're not going to necessarily use all the inputs and outputs to these modules. So as a result, all inputs need a value, and it's okay not to assign value to outputs. So inputs need a value. You can leave the outputs floating. By all means, do not remove like signals from your instantiation template. It's gonna mess everything up. So use the universal 7-segment display. Use the FSM template as a starting point for the model for your state machine. And you're going to need a clock divider in this circuit also. So there's a couple clock dividers on Canvas. I want you to use the one with testing in it. I think it's called something like 2 to the n test. And that's going to help you make it easy for you to simulate your circuit if you need to. And chances are you'll need to simulate your circuit in this one. The problem is when you simulate your circuit, you're going to have to use the fast clock or the board clock. When you're running it on the board, you're going to have to divide that clock, which is why you use the clock divider. So this is the top level circuit. Essentially, it has a clock. The inputs are a clock and a button, and that's it. And the outputs are the anodes and the 7 segments. And I also asked you to output the addresses onto your LEDs, so you're going to have to use at least 4 of those LEDs, which, fills up the, 16 location RAM. So this is due 6 class meetings from the day it is assigned, so that's essentially April 14th. By all means, get started on it early. It's not something you're going to whip out in an hour or two. You're going to have to actually work on it. So please get started early. Ask me questions if you got them.